A lot of people have wanted to know how you can calculate forces between wires that are parallel to each other but may have currents going in different directions. In this video, I'll show you how to do that with vectors. So imagine we have a situation like this where we've got a 5 amp wire with current going into the page, another 5 amp wire with current coming out of the page, and another one with current going into the page. They're arranged at equal distances from each other. Here the distance is 1 centimeter, and here the distance is 1 centimeter. And here we're told that this is a 45-degree angle from the vertical. So the question is asking, what is the force per unit length on this wire in the center here? And so to solve this problem, we're going to have to consider the force of this wire and the force of this wire on this central wire here. And we're going to have to use vectors and resolve them into x and y components. So let's talk about the steps. So here we go. First, we're going to sketch the forces and just take a rough look at what these forces should be producing as a resultant vector. That'll give us an intuitive idea about what to expect. Then we're just going to calculate the magnitude of the force per unit length from each of the wires. Since they have the same amount of current, all the wires do, and the same distance, then all I have to do is calculate that once, and I can use that number again and again. Then the last step, third, is broken down into sub-steps. So what we're going to do is basically take these forces, these force vectors from this wire and from that wire, and break them down into x and y components. Then we're going to add all the x parts together and all the y parts, keep them together. And then we're going to get the resultant vector by collecting the x parts and the y parts to determine the length, and then taking the ratio of the x parts and the y parts to determine the angle. Okay, let's go. So let's take a quick sketch of the forces like this. So if we know this wire has current going into the board, and this one's got current coming out of the board or the page, then that means they're going to repel each other. And so what we have here is this red arrow, which will represent the force exerted by this wire going into the page against this wire here. So it's going to look like that. Likewise, this wire is going to cause a force that repels, and so we're going to have something along that line of connection pointed in that same direction. So we've got these two red arrows, and they'll be equal in magnitude because, again, the current here is equal to the current here. The distance here is equal to the current, or to the distance there. And so what I can do is I can take one of these vectors and just put it right there and basically sketch it, okay? If I put it at the origin, now I can take this vector and I can bring it over. So I can put it over here like this, adding them head to tail. So I create a chain of vectors. And now to find the resultant vector, what I do is I draw from the origin to the end of the chain, and that will be a rough idea of what the resultant vector will look like. So that gives us a rough idea of what its length is and its orientation, what its angle will be. Okay? So now let's calculate the magnitude of one of those red arrows. So the formula that we can start with is something like this. This would be given to you on the exam, and what we're going to do is calculate the force per unit length. So we're going to divide both sides of this equation by L, and so we get force per unit length. Now, why do we do force per unit length? Well, it turns out that if I'm only looking at 1 meter of wire, I might have, let's say, 1 Newton of force. But if I'm looking at 2 meters of wire, then I'm going to have 2 newtons of force. So it depends on how much wire we're looking at. And so one convenient way to kind of represent the intensity of that force is to say, how much force do I have for a given length? So that's why we use force per length. And when we look at this formula, what we're going to get is something like this. We're going to get the constant mu naught times the current from each of the wires divided by 2 pi times this distance r between them. So we can plug in the values for that. This is mu naught, this is the current of the first wire, current of the second wire, and this is the distance between them. When we do that, we get this value of 5 times 10 to the minus 4th newtons per meter. So this is the length of the red vector, or the magnitude of the red vector. Now let's go to the next step. So we know that that's going to be the vector of this one pointing that way and of this one pointing that way that we saw earlier right here, okay? Now we have to resolve these guys. So we're going to break it down into x and y parts. So for this first one right here, this one's pointing just straight down. This is along the y-axis. We don't have to resolve it. It's already resolved in a sense. It has no x component. It only has a negative y component. So I'll sketch that by this blue dashed line here. This arrow, on the other hand, is tilted at 45 degrees from the x-axis. And so what we've got to do is basically decompose it into an x part and a y part. The x part is positive, the y part is positive. So I sketched those parts right here. And so graphically what we're going to do is we're going to group together the y part, so that's this part, with this y part here. That's how I've represented it here. And then here is the x part, and we have no other competing x parts, so we're just going to keep that the way it is. So we've got to add these guys together. So we've got to calculate their magnitudes first. So let's do that in the next step here. So we're going to add the x parts together and the y parts together. So let me zoom in on this part here. So this is where a lot of the vector stuff comes in. We know that this red arrow has a certain length of 5 times 10 to the minus 4th newtons per meter. We know that this angle is 45 degrees. So how do we get these components like this? Well, it turns out that we can do it just by taking the length of this and multiplying it by either sine or cosine of this angle 45 degrees. How do you know which one? Well, here, this side here, the x side, is basically touching this angle here. So we'll call this the adjacent side. So cosine is adjacent over hypotenuse, so that's why we're going to use cosine here. Now for this side here is opposite to the 45 degree angle. I have to go all the way across from the 45 degree angle to get over here. So because it's opposite and sine is opposite over hypotenuse, I just multiply it by sine 45. So when we do that, when I take this number and multiply it by the sine of 45, I get this number, 3.5 times 10 to the minus 4th newtons per meter. And likewise, because 45 degree angle, the sine and cosine are the same, when we do that, we get the same number here. So those are the lengths of the x and y components, which we can draw here, roughly speaking. It's that and it's that. Now what we're going to do is we're going to collect these y values. So we've got this y value from previously, and now we've got the y component of that other one. Now this one was minus 5 times 10 to the minus 4th. This one was plus, because it's pointed upward, 3.5 times 10 to the minus 4th. We add these guys together, and we get 1.5 times 10 to the minus 4th. So that's basically going to be this vector, added to this one. We're going to get a negative vector going down, something like that. Okay, so that's what we have. So that's the y total. As I said before, the x total, we don't have to worry about that. There's nothing else competing with that, so we just carry that over like that. And that's what we have for the x. So let's go to the next part, which is the last part, which is getting the resultant vector. So to get the resultant vector, let's just zoom this in. This is what we previously talked about. Go back to this. This one. Okay, here we go. So what we're going to do is basically add these guys up. So this is the part, minus 1.5 times 10 to the minus 4th. That's this, okay? And then this is the x part that we just preserved. 3.5 times 10 to the minus 4th, that's this. So adding up this x part and this y part should give us the resultant vector. And notice that it's pointed roughly in the same direction as what we got with our intuitive sketch that we did in the first part of this. All right, so the first step that we can get is, what is this angle here? Well, this angle is indicated by the ratio of this side to this side. So this angle here has an opposite side, that's this, the 1.5 times 10 to the minus 4th, and it has an adjacent side like this, 3.5 times 10 to the minus 4th. So the tangent, which is opposite over adjacent of that angle, should be this side over that side. Now that means I can take the arctangent of that ratio to get the angle. And when I do that, I get roughly 23 degrees. So it's tilted roughly 23 degrees below the positive x-axis. That's the angle of this. How do I know the length of it? Well, I get the length by just basically using the Pythagorean theorem. Since this is a right angle in here, I know that this is the hypotenuse, and this is one leg, and that's the other leg. So if I square this, and then add it to the square of this, and then take the square root of that, then I should be able to get something that gives me the length of the hypotenuse. So the length of that hypotenuse is the square root of the x components squared, or the x component, which is just this one, and the y component squared, which is just this one. And if I do that, and I'm careful to copy everything down properly in my calculator, I do that, and we go all the way through, take the square root of it, I get 3.81 times 10 to the minus 4th newtons per meter. And now I can basically look at this and say, here's the resultant vector. It should be tilted down below 23 degrees from the positive x-axis and have a length roughly like that. And like I said, that roughly agrees with our initial sketch. Now, a point about this is you have to be very careful with the calculations. It's easy to make a mistake. And in fact, I did an earlier video and I copied this down incorrectly. I said it was 2.25 times 10 to the minus 7th, and I got the wrong answer. And a student pointed it out. And I'm glad that that happened, and I'm happy to correct it here. And this is typical of any type of lengthy calculation that you might be able to do on a test. You should check everything. And I'm glad that I had someone checking mine. I hope you can have the time to go over it a second time in the exam. Hopefully this was helpful to you, and I wish you the best on the upcoming exam tonight.